Thank you for the introduction. As already explained, the bachelor is already done, so I'm credited already. Today I would like to talk a little bit about the technology behind, but first, for those who do not know Riegl in detail, we prepared a couple of minutes video just as a company self-introduction. So it will be about the company, it will be about some benefits, about what LiDAR give you as additional data attributes. Then about the sensors, of course, a little bit. I do not want to talk too much. And last but not least, also about the data. As you know, we are working in these 5 segments about terrestrial, mobile, airborne, unmanned, and finally also industrial laser scanning. So we do offer products from all kind of these segments. But before we go too much into detail about that, please enjoy this couple of minutes video, and we'll see you later.
As one of today's leading manufacturers of laser measurement systems in the world, Riegl provides innovative technology for a wide range of mapping applications. Terrestrial laser scanning is used for ground-based applications, such as architecture and cultural heritage documentation, open-cast mining, or public safety. Airborne laser scanning enables data acquisition of large areas by means of fixed-wing aircraft or helicopter. Mobile laser scanning from moving platforms allows for both 3D and image data to be captured while moving past objects, be it from a car, boat, or rail platform. Laser scanning from unmanned aerial vehicles is a particularly efficient, modern version to acquire data for a variety of surveying tasks. The production of all Riegl devices and systems takes place in Horn, Lower Austria. Supported by state-of-the-art technology and equipment, the latest innovations are created and manufactured. Each individual component is carefully crafted and thoroughly tested. Each device is required to meet the highest quality and performance standards. Research and development and a large part of production are still located there today. The large-scale outdoor area is used for testing and calibration. In 2006, administration, sales, and marketing moved to a turn-of-the-century building in Horn. In 2012, a state-of-the-art CNC production facility became operational in a newly constructed building in Horn. Additional offices in Vienna, Salzburg, and Styria completed the presence in the German-speaking region. Just in time for the 40th anniversary, the groundbreaking ceremony for an additional manufacturing building, which will almost double the currently available operating space, is taking place. With the addition of a new Cessna 206, the Riegl aircraft fleet required for test and calibration flights is also growing. The Riegl team today comprises more than 220 technicians and other highly qualified and motivated employees worldwide. Riegl manufactures laser scanners and systems for commercial use. Laser scanners capture surfaces in a pattern of millions of measuring points. The resulting 3D data is made accessible in the form of a point cloud, which is a photorealistic, precise representation of the scanned scene. Riegl devices make use of pulse time-of-flight laser radar technology in multiple wavelengths. High product reliability has always been a priority for Riegl. Every single product has been put through its paces. In production, we rely on the latest technology, high-quality components, precision, and care. Riegl customers can expect sensors and systems of the utmost quality. The latest product segment Riegl has delved into is comprised of more and more LiDAR sensors for unmanned aerial vehicles, UAVs, and even Riegl's own UAV measurement platform, the Recopter. New fields of application in every segment are opening up all the time. Riegl is the innovation leader in airborne laser scanning with solutions for nearly all imaginable fields of application. Combined with the appropriate Riegl software packages, precise, meaningful measurement data and image data are made available for further processing. A new generation of terrestrial 3D laser scanners is available with extraordinarily long ranges, extremely fast and accurate, having high information content for each single measurement, and, of course, are extremely user-friendly with application-specific software packages and cloud connectivity. Riegl offers a wide range of application-specific solutions for mobile mapping. Innovative firmware and software solutions ensure that the advantages of Riegl's proprietary technology can be optimally utilized. The company headquarters in Horn, Austria is the central hub supported by Riegl main offices in the United States, Japan, and China, and the latest addition to the network from November 2018, the newest subsidiary, Riegl Australia.
So I stop here. As you've seen, it's a lot about the company. You see it's expanding. We want to start building a new production facility. We're expanding the market, so we can see even all the LiDAR sensors in general are quite demanding on the market. We're here to talk a little bit about the unmanned application, unmanned laser scanning. So I'm more focusing on like the lower end, so everything which is like up to a maximum takeoff mass of like 20-25 kilogram. And it has already been explained, so I do not want to talk too much about the system. It's more about the sensor, about the technology. As you can see, like the product range we offer on the unmanned sector is quite wide already. From the MiniVUX-1 UAV to the DL for the downward looking, up to like the VUX-1, we can offer like from 1.5 kilo up to 3.5 kilo, a complete range. Like the key figures of all this system, especially for unmanned purposes, is mainly weight. So if we take like the UAV, the MiniVUX-1 UAV, just a single sensor, not about the system specification, we're talking about like 1.6 kilo, about 3.6 kilo about the VUX, and 2.5 or 2.4 with the MiniVUX-1 DL. As you can already see, there are like a few differences as with regards to field of view. So we're talking about 360 degree on the sensors on the left and right hand side. We're talking about a 46 degree field of view on the MiniVUX-1 DL, which is especially prepared for fixed wing, long flights from 100 meters altitude, especially for transmission line, power line survey. There are two other sensors as well, which we do offer, like a very niche market, like the BDF1, and quite recently introduced at Intergeo in Frankfurt, our VUX-240, which is almost the same size as the VUX-1, so we're talking also about 3.6 kilo, but it has a spectacular pulse repetition rate and a measurement rate up to 1.5 million measurements per second. It has around 75 degree field of view, so it's a little bit comparable, something between like a 360 and the 46 degree. But especially if you can fly up to a couple of 100 meters, it's totally enough for the survey. Just one slide on the what point density you can get. There will be also some information about the VUX, the DL, and the MiniVUX-1 UAV. Just on the VUX-240, by measuring or by flying around 100 meters above ground, 10 meters per second speed, this could be a faster multi-rotor system, we can gain up to like 1,000 points per square meter. This is a lot. So we're already starting about handling the data. Of course, especially flying with a fixed wing, we can almost increase this number by double, so around 20 meters per second. Even point density is almost like 500 points per square meter. If we put like the higher end series in comparison about the VUX, the VUX-240, the long range, so we do offer like a series from the VUX-1 LR and the VUX-1 UAV. The sensors itself looks exactly the same, but of course they differ, especially in pulse repetition rate, of course also in terms of accuracy. The maximum measurement range, of course, like up to 2,000 meters with the lowest pulse repetition rate. The rest is almost the same, but of course, all these three sensors, they offer like, or they have around 3.5 kilograms. So they almost have the same weight. Even the VUX-240 is a little bit larger, but it's made out of carbon fiber, so it's getting a little bit lighter at the very end. If we take like the MiniVUX series, like the UAV and the DL, and put it in comparison, the values are almost the same in terms of pulse repetition rate, 100 kilohertz, in terms of accuracy, maximum measurement range. But of course, what it's differing from each other is mainly the weight. So we're talking about 1.5 to 2.5 kilogram, and then especially it's the field of view. So even having the same pulse repetition rate, by narrowing everything down to 46 degrees, you can increase the point density a lot, which is quite good for power line survey at the very end. When it goes to point density, if we fly, or this is like an actual data set or values out from an actual data set, where you can have same altitude, same speed, it was flown with a multi-rotor system, you can get with the MiniVUX-1 UAV 35 points per square meter, with the VUX-1 up to 200 points per square meter, and the MiniVUX-1 DL around 300 points. So you can get more, but of course, if we're talking about the application point of view, if we're talking about corridor mapping application, wide area mapping, then of course considering 360 degrees, so the sensors on the left and right hand side, is even more practical because it can be more easier to use, easier to deploy, and at the very end it's more efficient. So this is like a scanner selection guide we selected. As you can see, like all sensors are not suitable for every part or for every application, especially if we're talking about glacier and snowfield mapping. When we're talking about the wavelengths, so the MiniVUX series, so the UAV and the DL operate on a different wavelengths than the VUX-240 LR and UAV, and that's why it's also better. Even on the highest pulse repetition rate, you can get the maximum range out of it. So you can also get snow and icy, or you can measure snow and icy terrain with the other sensors, but the range is on the very lower edge. So we're talking about like 10% reflectivity maximum. So I don't want to talk too much about the sensors because it was already explained before. I want to focus a little bit more about the technology, what data attributes we deliver, what's behind, so that you get a good feedback about what the sensors can offer. So first of all, the technology itself. So they are, of course, we started with airborne scanning, terrestrial scanners followed. Especially on small ranges, indoor applications, a lot of sensors make use of phase-based principle. We do make use of the pulse time of flight system, which is very good for long-range survey, but you can of course also make use of indoor, but our sensors are not very good at the very short range. So it's a scanner that can offer that can be used everywhere, but of course you need to take care about what's needed. And then, of course, we distinguish again between a discrete return and the echo digitized LiDAR, and what's that I would like to explain a little bit in the further slides. So it was shown very short in the video what is the time of flight, what is about the multi-target capability, what the sensor offer, the multi-return. So what we do is we send out a pulse and we reflect a pulse. This would be like the easy measurement principle. But of course, if it's something, any object is hidden in front of the surface we would like to measure. We're talking about multi-return system. So you send out a pulse, you will get a number of pulses. These number of pulses are limited on the sensor point of view. So the MiniVUX-1 series can offer up to 5. On the VUX-1, we are more or less practically unlimited, but the practical number is like up to 10 to 15 points per one single laser shot, so 10 to 15 echoes per one single laser shot. And so how is this done? So what we do is, especially coming from airborne, we always talk about waveform processing. We're talking about full waveform. On the MiniVUX and VUX series, we're talking about the online waveform principle. So what we do is we already post-process these returns during data acquisition. So what we do is we digitize the waveform, and at the very end you will get a peak on your multi-return system, which gives you like P1 to Pn, so up to a couple of points, a couple of echoes, and all this is done in real time. So the practical view, if we talk a little bit about that, if you have like a cornfield, vegetation, it's especially about penetration through the vegetation. You get your waveform, it's digitized, and we overlay this. And at the end, you get your first return, you get intermediate returns in between, and you get your true return at the very end, which is your ground surface, which you're mainly looking for. If we take a practical example, this was measured by terrestrial scanner, so not UAV, honestly. But if we took just a crossing through, you can even see that if we colorize with blue, this would be my last return. We would have single returns if like the full laser beam hits the target surface, but also first return and intermediate returns in between. What can be seen in the next slide afterwards, if you take like this, I don't know if it's quite good visible, but this is a net here in front of like this rock fall. If we take a crossing through this rock fall, you can clearly identify like the first returns, which is also used for power line survey. So especially all the power lines always give me a first return or single return. The power line itself could not be a last return, which is also good if the third-party software is classifying or it's using these data attributes afterwards for filtering, for extraction of the data. So that's about the LiDAR principle. To go a little bit in detail about what additional values does Riegl, does the point cloud we produce offer. So I don't know if all of you heard about like the pulse width. We call it deviation. The pulse width represents like at these, at the full width, at half the maximum sampled signal, and it's an invention. It's a quality attribute that Riegl has introduced in additional to the point cloud. So additional to each echo, we also acquire this pulse width, and it gives you a reliability for the range reading. So what's the actual practical example on that? You take a tree, you take vegetation. If you take a look on all the points, you can see it almost looks good. But if you start filtering by using this pulse-shaped deviation, you can see that there are a lot of noisy points. Noisy point, it's not like, it's not a true value because, as I have explained before, as it's a multi-return system, between these multiple returns, there need to be at least a few centimeters, a few dozens of centimeters, so around 25 to 35 centimeter, where we clearly can distinguish between two echoes. So if we cannot clearly distinguish between these two echoes, we identify it as a very bad point, which means the value of this deviation, the value of this pulse shape is very high, so we can use it for filtering. There's no specific unit, so it's a value between 0 and 65,000. If it's very close to 0, very close to 1, it's a very good target. If it's higher than that, around 10 to 15, it's a very bad target, which could be filtered. So at the end, you get a very clean point cloud out of that. Additional to that, in a lot of articles, always it's reading about calibrated reflectance, calibrated amplitude reading. What is it? Mainly the airborne sensors make use of intensity. By using a calibrated amplitude, intensity, you can also make a reflectance out of it. So intensity, very important, is a range-depending range reading. So as you can see from short range, here colored in red, on the very far away it's colored in blue. If we switch now to reflectance, which is range independent, you can clearly see the target surface. So if we're talking about like traffic signs, they're very high reflecting targets. So it doesn't matter in which range, here, 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 or even further away, which we can see in this picture, they have always the same reflectivity value, which is taken out from the amplitude reading. The houses, the rooftops. So reflectance gives you much better feedback from the point cloud as the amplitude. Another practical example, if you take out here, this is again from a terrestrial, so it's not the UAV one, you can see traffic signs from all the ranges are colored in a very, in this case it's red, which indicates it's a very high reflecting target. On the other side here, again, even further away, the color is always the same, colored in grayscale. Especially if you take a look on a comparison between an RGB image, so taken by any photograph or any camera, and the calibrated reflectance, you cannot identify in this case it was a graffiti, beneath. So by using the reflectance information, you can clearly also see what's behind. To give you another example, again, on the right-hand side, it's the RGB image. And especially if you take a look on those areas here, you can clearly see that they got a problem with water. So every stone here has a different reflectance information, which indicates also water, because also if you measure the eye from the human face, the water or the eye is containing a lot of water, you cannot measure it. So especially here, they are distinguished between each other, and they really got a problem with water inside this facade here. However, I want to go very quickly about this candidate adjustment. I don't want to talk too much, but the point cloud creation is the one thing. You can get it from one line very easily, but the main problem you get is as soon as you have multiple flight lines, if you have multiple projects which would be combined. So especially about the trajectory errors, about how this being affecting the point cloud. So if we take all the accuracy levels into account about the sensor, about what do we have about the scanner coordinate system, which is very accurate and very precise, down to a couple of millimeters. The platform trajectory, it doesn't matter if it's an APX-15 or an APX-20, which comes from the GNS, compared to the LiDAR, it's comparable low, but this is how it is, from centimeters to decimeter. And last but not least, it's about system calibration. So how does the lever arms and orientation is being affected, which are also quite highly accurate and precise, being measured up to millimeter, millidegree. And if we take all these three accuracy levels into account, we come to the conclusion that we have to modify the point cloud, especially in this case the trajectory, to optimize the output. So what we get is, this is the Colosseum in Rome in Italy, acquired by a mobile survey. You can see like it fits here, so these were 3 overlapping passes. We have a fitting of the point clouds colored in height, 10 centimeter, 20 centimeter, 40 centimeter, 70 and 80. So if there would be just like a point cloud matching algorithm, it's really hard to fit all these point clouds together reliable. So we have also a software tool developed that fits or that merges this point cloud on modifying the trajectory. So we do not modify the range information of the LiDAR, but we do modify the trajectory. We more or less bend the trajectory, which again provides a much reliable data at the very end. So we modify the geographical position in the air, which of course results in a very more accurate data if you overlap the point clouds. So this is how it works from a mobile survey. Again, you have overlapping strips. You have a couple of flight lines or whatever. You merge it by trajectory adjustment, and again, this is what you're seeking for. You would like to have one full point cloud that you can use for further extraction of the data. Last but not least, just some slides about what projects we have done at Riegl, about infrastructure projects. So this is pretty known already, which we have flown by UAV, with the VUX-1, with the cameras, with the dual camera system, colored here in reflectance, about open pit mining. It's a dumping area from a railway tunnel that is built, where they dump all the material by merging data from the very beginning and 2 years later, where you can see that they want to dump the area over here, and you can even see like the streets they are building by using cut and fill volume comparison, that the fitting of the data works pretty well. Last but not least, also transmission line, power line, substation survey. LiDAR is perfectly suited for. So photogrammetry is always not so good for power line survey, but the really key is the combination. So if you have photogrammetry combined with LiDAR, this gives you really the tool to provide both. So last but not least, I talked about the multi-target return, about vegetation, about the penetration through the vegetation. What you can see here is just one tree out of a huge project, but this was acquired from a lower altitude with multiple strips, and what you can see is all the details. It's from multiple sites, so it's not only one strip. It has been 4 strips that has been overlapped to each other, and at the very end you get a very clear picture from the forest. So what to do with this data? We have a customer in Austria that are very much based on research, but especially for vegetation purposes. So they developed together with another company software algorithm classification methods to extract information out from the vegetation. So what you get here is like, that's the pure point, the point cloud, the colorized point cloud, processed by each single tree segmentation, in this case, and also colored by height. And what they get at the very final end is they can also count the trees based on height information, but the very important task is they can classify it. So what they do is they cut the data in a specific range, around 1.5 meters above ground. Afterwards, they calculate above and below to the ground surface. And at the very end, they can really classify, they can calculate biomass. It's really, really ridiculous what you can really do with the data if the point cloud is dense enough. If you don't have the density to calculate the trunk of the tree, you won't be able to post-process such results. So all the sensors are suitable, as already explained before, for a couple of, or for multiple variation of applications: civil engineering, power line survey, terrain mapping, infrastructure, open pit mining. I don't want to go too much into that, just the outlook for the future. We have already and we will continue to provide sensors for the unmanned market. We can really see that especially the influence for UAV-borne LiDAR sensors will increase. Drones are coming. Regulations especially are establishing on the market. And based on that, we are also open even to fly vertical takeoff and landing beyond line of sight, so operation gets more efficient. And this is where UAVs will also change the way how we collect data from now on. So I hope you find the presentation valuable, and thank you very much.